Hey, welcome back. Today I'm going to explain three big ideas in this tutorial, but before that, let's do a very quick fun exercise. What do you see in this picture? Pause the video for 10 to 20 seconds and try if you can spot something interesting in it. Let me help you if you are having some difficulties. The object of interest is inside the red boundary. Pause the video again if you need to. If you are having some trouble seeing that interesting object, then let me help you here. There seems to be a dog or a calf with its head down. Here are some pointers to its head, ear and mouth. Take more time if you need it. Pause for a few seconds. Now, what is interesting is that if you are able to see the animal now, you cannot unsee it. Even more interesting is that if you would see a similar image with some other animal, you would be able to spot that animal relatively faster than the time you took with this image. So, what is the magic behind it? To demystify that magic, I introduce you to a paper titled Amortized Inference in Probabilistic Reasoning by Samuel Gershman and Noah Goodman. Their take on what we experienced with the image earlier is that to find an interesting object in that image, our brain performed quite many computations. They called these computations queries and argue that our brain stores the result of these queries in its memory. Maybe it's a long-term memory or a short-term memory, we don't care about for our discussion here. And then they associate a specific term with this behavior of our brain and call it amortized inference. Now, most likely you have heard this word amortization in the context of the home loan or mortgage. As such, amortization has several meanings based on the context it is used, but the interpretation that is relevant for our discussion is that amortization here implies spreading out the expenses over a period of time. Expenses in our case is that of computation. Once we have done some computations, a portion of it can be used later for future inferences, and hence the authors call it amortized inference. We'll come back to the paper again, but for now we want to be inspired by this behavior of our brain and investigate if we can achieve similar behaviors like this in the context of our machine learning based models. Let's start with some terminologies, notations and conventions. Here I have a variable called x. If I put a circle around it, it means that it is a random variable. A random variable has various possible states, and with each state is associated its probability of occurrence. In other words, we say that a random variable has an associated probability distribution. If I fill this random variable with some color, then it means we can observe the various states of this random variable. Now, when we are doing statistical and or machine learning modeling, we consider that besides x, it would be beneficial to include some other random variables. But the twist is that we cannot observe them. Generally, symbol z or z is used for these unobserved random variables. The stuff to ponder over here is to see if there is a relationship between this assumed unobserved random variable and the observed variable x. As such, there are a few different ways we can formulate this relationship, but the one that is quite often used is to consider that z is about a physical phenomena that caused x. For example, x could be the measurement of a location of a robot in a room, whereas z could be the velocity of the robot. Clearly, speed or velocity has an impact on where the robot is going to be. And so if our model has a way of taking both observed and unobserved variables into consideration, we have a possibility to get better results. These unobserved random variables are also called latent random variables, and the models that take into consideration latent variables are called latent variable models. There are many famous examples of these types of models, however, they often go by different names. For example, state space models are latent variable models. I have a tutorial on Kalman filter which assumes a linear Gaussian state space model, which is also a latent variable model. And if you want to go into the details of that, I have a tutorial. So if you need, you can check it out. Now the obvious question here is how one determines these latent random variables. But quite frankly, before we go any further with how to determine, we need to answer what does it mean to determine the random variable. Determining here means finding the parameters of the distribution function of our latent random variable. For example, if we believe that our latent random variable follows Gaussian distribution, then we want to determine the mean and variance of the associated Gaussian distribution. With that settled, if you look at this picture, I'm not sure if there is any other option but to possibly use the observed random variable to determine the parameters of the distribution of our unknown random variable. Notice the direction of the arrow has flipped, and note that the arrow is now a dashed arrow. The process of finding unknown or hidden random variables using the known or observed random variables is called inference. Quite often people use the terms inference and prediction interchangeably, but they don't really mean the same thing. Now, one very famous algorithm to perform this inference is an algorithm called expectation maximization. In this tutorial today, I will not go into the details of this two-phase algorithm as it has been explained many times over the last 40-50 years and maybe even more. However, the part I want you to pay attention to is that this algorithm requires you to run one of its steps for each observation. That is, the expectation step is going to run for each observation. Even if you don't know this algorithm, or really there is no need for you to know it for our discussion here, just notice that this algorithm involves for loops. And in computer science, we dislike for loops. As such, more than for loops, we dislike nested for loops. So look here, you have a while loop and then there is a for loop inside the while loop. So not only we have nested for loops in this algorithm, but if you also have a large amount of data, this algorithm does not scale properly with respect to computational requirements. In brief, in big data realm, this naive implementation is a recipe for failure. And therefore, to find some remedy and inspiration, we borrow the wisdom from this paper. The authors here do talk about expectation maximization style traditional algorithms for inferences, and they mainly point out that these are memoryless algorithms where previous computations are not being considered, which then leads to either repeated or wasteful computations. Now they recommended that we get inspired by our brain's amortized inference, that is, equip our modeling strategy to have the notion of smart memorization and or use cache inferences from past to be more efficient. By now, I hope you have caught on the goal of this tutorial here. The goal is that we ought to find the parameters of z from x in an efficient manner. The keyword here is efficient. And to take the first step in this direction, I suggest that we use a function that takes the realizations of random variable x as input and gives you z as the output. Like any function, it would have parameters that would interact with the input to make all of this happen. Just before proceeding any further in this direction, one little minor change here. I'm interchanging the location of random variables. I like to see the inputs to a function coming in from the left side just to keep my sanity. And so note that the arrow direction has changed as well. In nutshell, no functional change so far on the screen. Simply, I have changed the location of random variables. So coming back to the main event, hopefully you have started to think about how one creates such a function. Now, instead of creating a mathematical model of this function by ourselves, we should think in the direction of learning it. And in modern times, neural networks are the best candidates for that. Especially when I have already suggested that we need to solve the inference problem in latent variable models in the big data realm. So we will now spend some time first building a neural network and then see how to train it such that it learns its weights that would enable us to do amortized inference. Here is the simple feed-forward neural network that takes a 6-dimensional vector as an input and generates a 2-dimensional output or prediction. This also means that in this setup, we are suggesting that our random variables are multidimensional or multivariate. I'm sure you would not have much problem with me using 6-dimensional input vector. You can easily presume that samples from the dataset I'm using are 6-dimensional. So input is easy to understand, but what may bother you is how and why I selected the dimensions for Z. You see, we don't even know Z. So how the heck I made this choice? And the answer to that lies in hyperparameter search. That is, during your experiment for a given data set, you would figure out the dimensions of latent variable by doing some sort of a grid search or an advanced version of finding the hyperparameters. And maybe the feelings that you get from your intestines, also known as gut feeling. Actually, more than the dimension of the prediction vector Z, I want you to be concerned with another aspect. As I already told you that we are interested in determining the parameters of random variable Z. However, in this setup using neural network that I have so far, we will simply end up predicting a Z vector for a given X vector. Whereas what we really want is that our neural network predicts the parameters of the distribution of random variable Z. This part is very important to understand, and hence I will go slow here and dwell on it a little bit more. And reason for me dwelling a little bit more on it is because based on my experience explaining this to some of my colleagues, I felt that there were some gaps in their understanding of what is the desired behavior that we are after. And I believe those gaps primarily stems from the limitation of the notation and the graph of latent variable model that you see in the bottom left. Again, one more time. The current neural network setup will predict a Z vector for a given X vector. Whereas we want to have the capability where for a given realization of a random variable X, we want to get as many realizations of Z as we wish. But before we go in that direction, I still want to point out another approach that you can take or the direction that you can think in, which is that you may very well consider that the output of our neural network is an average value of all possible realizations of Z. Well, first I need to correct my phrasing here. When we deal with random variables, we should say expected value and not the average. And as such, it is not a totally incorrect direction to think in, and we will use this kind of a reasoning later in the tutorial. But for now, we really wish to predict the distribution of random variable Z for every single realization of X. But again, like before, I must first refine my phrasing of the goal here for more clarity. Instead of saying predict the distribution, it is better to say that we are interested in predicting the parameters of distribution. Because once I have the parameters of the distribution, then I can generate as many realizations of Z I want. And this does open a can of worms or can of questions for us. And the first one is obvious, and it is to first agree upon the type of the distribution. Since in this example we have a Z vector that is a multi-dimensional random variable, we should think in the direction if all the dimensions are going to use the same type of distribution. Of course, every dimension will have its own parameters, but it is interesting to consider if they are all of same type. If they are all same, it would really help with the computational needs, as potentially we can do some vectorization. And finally, are these dimensions of our multivariate random variable independent of each other? And this has a huge impact on the training setup. This notion of independence between the dimensions of the random variable vector could be a boon, but in some situations could be a problem. Now, as it is the tradition, we again use our gut feeling and or some hyperparameter search to address these concerns. For our needs, we will assume Gaussian distribution for random variable z. Every dimension as such is going to follow a Gaussian distribution. They will have their different parameters, but they will be all of type Gaussian distribution. And finally, the dimensions are going to be independent of each other. Now, these assumptions that I have made are helpful just from educational point of view, but reality is that these are the assumptions are also made in many number of experiments that are out there. So the assumptions are not just out of a whack here. With the assumptions about random variables out of the way, I modify our neural network to now use 4 neurons in the output layer. The neurons are now outputting the mean and variance for each dimensions. We have 2 dimensions for our z random variable, which means we have mu and variance for dimension 1 and mu and variance for dimension 2. That said, the way I have assigned the output neurons may disturb you a little bit. You may or may not like it. For example, you may have liked to see the output neurons labeled like this: mu and variance for dimension 1 and then mu and variance for dimension 2. It looks a little bit pretty here. However, from programming point of view, this good looking arrangement will be tad bit problematic, and I will make a case for it when I will walk you through some code snippets. Therefore, for now, I revert to the original arrangement. But there is an issue here. The problem is that we are saying that the last 2 neurons in the last layer are supposed to predict the variance parameter. Now, variance is supposed to be a positive real number, and we may have some challenges constraining the output of the neuron to be a positive real number. Truth is that there are ways to constrain the output of a neuron, but here we will take a different approach. We will expect the output of these neurons to be log variance instead of variance. And we will consider that we are expecting log variance when we will try to use these predictions of the neurons. Here is one more minor modification. This is because log of something squared can be written like this. So in nutshell, we are really expecting our neuron to predict 2 times log standard deviation. And finally, this is how you would use these predictions. Note that in this setup, the stylish looking n is for normal distribution or Gaussian distribution that takes mu and standard deviation as the input. So to first cancel the 2 in 2 log sigma, we first multiply it by 0.5. So half and 2 will cancel each other. And then we will pass the result to the exponentiation function, which should cancel the log, leaving us just with the standard deviation. Little sweet, cute, crafty trick. Now, enough theory and background. Let's see all of this in the form of code. I'm going to use Keras to write our neural network, but similar concepts are going to be applied for PyTorch as well. This is our first layer, the input layer that takes 6-dimensional vector. Here I have added 3 dense hidden layers and a dense layer that would output a vector whose entries are mean and log variance. Note the number of neurons in this layer is 4. Now we simply create the Keras model, supplying in the input and the output. We will also plot it to see how it looks. There should not be any issue understanding the generated graph now. Now let's pass some fake inputs to this neural network. And here we have the output. Hopefully you can now appreciate why it was a good idea to keep mean values, the mu's, in the first part of the vector and log variance in the second part. It made the indexing or the segmentation of the vector much more easier. Otherwise, in graph mode, the indexing could be difficult, if not impossible. And finally, we feed the values into the random normal API of TensorFlow. Thanks to my arrangement of mu and var, log variance in the prediction vector, we could easily split the vector into two. But you know what? It would be even a better idea if we don't have to split it in the first place. So I'm going to show you how you could do something like that. So here is our code so far. This is how we wrote our model with the layers in it. But I'm going to rewrite it in a just slightly different way. So the one in the bottom still looks like our original code. It only has 5 lines so far, but you see there is no change. But now note that instead of line number 6, I have 2 lines, 6 and 7. Instead of one dense layer that predicted the vector for mu and log var, I have now 2 dense layers, one for mu and second for log variance. Note that both of these receive the output of hidden layer 3 as the input. This is what the plot looks like. In this arrangement, we do not have to do any indexing or segmentation of our vector. It's much more cleaner. And also note that there is no side effect or problem in this arrangement. Personally, I like to write it this way. So far, so good. But you know what? It would be interesting if the process of getting Z was also part of the neural network graph. So far, we have taken the predictions of the last layer and then we fed them into another API. Having this generation of the sample Z part of the graph have certain advantages, especially when you will deploy the model. Essentially, we are looking for something like this. Pay special attention to the connection between the second last layer and the last layer. The neurons in the last layer are called stochastic neurons. I will now show you how you would write something like this using Keras. Essentially, we will write a custom layer in which we would perform the sampling operation. Now, this layer does not have any weights. All it is doing is that it is wrapping the operation of feeding in the output of our predictions that is mu and variance, log variance, to the random normal API that will generate the sample. And you can control how many number of samples you want. And here is how you would use it as part of your neural network. You really have a layer. It's a custom layer that you wrote, but now it will become part of your neural network, as you can see in the graph now. Hopefully this all makes sense now. So we have the structure of our neural network nailed down. Both inputs and outputs are now clearly defined. But then, this is just a structure. For this neural network to do anything useful, we need to learn its weights. And learning the weights here is no different from what you would do with any other neural network. You will use a backprop and optimization procedure to achieve this goal. That said, the missing piece, as such the most important piece, is that for optimization procedure to work, you need a loss function, also known as objective function, also known as cost function. And for that, really we have a challenge. As such, a loss function is something that would take 2 inputs, the prediction of the neural network and the ground truth or the label. And what a loss function generally do is that it gives you a measure of similarity between the prediction and the ground truth, which is then used to compute the gradients, and then the optimizer uses those gradients to update the weights of the neural network. So again, the $1 million question here is, what are the inputs to the loss function for our problem? To help with that, here I assign some more labels or names to the outputs of our neural network to clearly identify our predictions and also the ground truth. The output of our neural network are the parameters of the probability distribution of random variable Z. We generally use symbol Q to indicate it, because Q is used whenever you are approximating things. And of course, predictions of a neural network are always approximations. Note that this also captures the joint distribution of dimensions of random variable. And more importantly, because we are using X as an input, we say that the output is a conditional joint distribution of vector Z given vector X. This is the prediction, but loss function also requires the ground truth as well. we generally represent the ground truth using the symbol P. Now, if you are thinking that we do not have access to the ground truth, you are correct. But I request you to hold on to this thought, as we will primarily work in this direction now to solve that challenge. But before that, we must answer the fundamental question of how one determines the measure of similarity between two probability distributions. You also know that the job of loss function is to give the error information, that is how dissimilar predictions and ground truth are. Loss functions and computation of similarity is easy to reason about in most cases, but here we are talking about finding the difference between two probability distributions, Q and P. And again, as I said earlier, the first fundamental thing to answer is how one compares two probability distributions. And the answer there is that if you want to measure the dissimilarity between two probability distributions, you will use something called KL divergence. If you already know what it is, then all is fine. But if not, then you would want to check out this tutorial of mine. In this tutorial, I explain not only the intuition about it, but also build its mathematical formulation from the ground up. Check out this tutorial if you think you have some gray areas. The type of KL divergence that we will use will be reverse KL, and this is how it is formulated. But as you already know, we cannot compute it because we do not have access to the ground truth, the denominator in this formulation. Now, whenever we are faced with a problem like this, one strategy that could work is to simplify a given complex mathematical formulation. And possibly we may find an alternative measure that may provide the similar results. And this is what I do in another follow-up tutorial to KL divergence, which is titled What is Evidence Lower Bound? ELBO is really the loss function that we end up using instead of KL divergence. In this tutorial, I show you the step-by-step animated derivation of it and with KL divergence as the starting point, and also explain why it can be used as an alternative to KL divergence. To understand the rest of the tutorial, it is actually important for you to have a good understanding of ELBO. And based on the comments that I received on this ELBO video, I feel that it is one of my most appreciated video, and I'm sure you will not be disappointed. So if you do not know what ELBO is or what KL divergence is, I recommend that you go and watch those two videos before you proceed. Assuming you have a good understanding of what ELBO is and or what it represents, our goal is to maximize the ELBO. Maximization of ELBO is equivalent to minimizing the KL divergence. However, in machine learning, we often like to minimize functions. So really what we do is that we minimize the negative of the ELBO. With that said, let's see if we have access to all the terms in the ELBO. The first term is our prediction, so no problem here at all. You can see that this is what our neural network is predicting, the term that is blinking. Now, the second term that is blinking now is called prior on Z. Prior is based on your domain knowledge or hyperparameter search or gut feeling. And again, if you have watched the ELBO tutorial, it will make sense to you. So point here is that this is also something you have access to. But the term that is problematic is the one which you see here, which is the distribution of X given Z. And by the way, here's the Z that we are talking about is the Z that is going to be predicted by your network, the network that we just created. So here it's not a good news. We thought that we have almost nailed everything, but we still do not have access to one term that goes into our loss function. By the way, this network, we are going to give it a name. We call this network that predicts the distribution of our latent variable Z, the encoder network. Now, what we can do is that we can apply similar thinking process as before. That is, we first seek to find a function that can predict X given Z as the input. This Z would be the result of the neural network that we already created, the encoder neural network. Essentially, we now envision another neural network that will be used to predict the value of X with Z as the input. So let me show you how that neural network may look like. So here in this neural network, the inputs are Z's and the outputs are your X vector. But this should make you wonder, why are we not predicting the parameters of distribution of random variable X? Actually, if you wish, you could, but it is also a compromise to assume that what this neural network will predict is the expected value of all possible realizations of X. We discussed this kind of a thing earlier in the context of random variable Z, but there we said, no, I am really going to predict the distribution of random variable. Here we are sort of happy and okay just learning the average value of all the realizations. And if we go with this thinking, we can indicate this by using X bar as the label for output neurons. And also then use a simple mean squared loss function to help this neural network learn. That said, you will not learn this neural network in isolation, or you will not learn it if it is separate from the previous network. You see, you still need the Z's. So in order to do that, we have to connect this neural network with our previous neural network. And by the way, we call this neural network decoder because it is decoding the X out of Z. So we have now encoder and we have decoder, and now we need to connect this encoder and decoder using the Z layer that we have. And this is how it is going to look like. For quite many of you, most likely you have seen this style of neural network. This neural network architecture looks very similar, actually identical to that of autoencoder. The difference here is that the latent layer is a stochastic layer. In other words, the encoder predicts the parameters of the distribution of Z. In traditional autoencoder, you do not have such a notion. Also, since in this setup we have approximated the true distribution with the approximate distribution, we have performed what is called variational inference. And this is why this network is called Variational Autoencoder. The loss function that is used is ELBO, evidence lower bound. The first part of the ELBO represents the reconstruction loss. In many situations, you can replace it with the mean squared error, as I explained earlier. And the second part represents the KL divergence between the approximated posterior and the prior. Once the variational autoencoder is trained, you can remove the decoder part of it, and that would give you the latent variable model that has the amortization properties. But by the way, you can also use it in a different manner, which is as such more famous. To use the decoder to generate new or different samples or variations of your samples. This makes VAE or Variational Autoencoder classified under generative models as well. As such, in last 3-4 years, we have seen a lot of innovations that build on VAE as the foundational architecture, and maybe I'll talk about them in some other tutorials. Finally, I want to bring your attention to one last aspect of VAE. You see, typically in your neural networks, you have what we call deterministic nodes, and you use optimization procedure to update the weights. However, even though the architecture looks like an autoencoder, it is different. It has some differences, and the primary difference is that we have a stochastic layer which has stochastic neurons. Stochastic is just a fancy way, but a better way of saying randomness. So now the challenge is how we can have backprop working when there are stochastic neurons in our neural network. The VAE paper talks about a remedy called Reparameterization Trick to handle this kind of a problem. Now, I don't want to simply tell you what it is because it is no fun without understanding the true problems the stochastic neurons create. Hence, I will explain it as part of a separate tutorial in which I will explain some challenges in general with neural network backprop and optimization procedures and how they escalate when we have stochastic neurons. And of course, the various remedies, including reparameterization trick that can be used. And with that, I end this tutorial and thank you for the time you've spent here. Hopefully, not only you now know what VAE network architecture is, but more importantly, you understand the kind of problems that it aims to solve. So, that's it. Goodbye for now. See you in another tutorial. Bye-bye.